University. All our contact information is up there. And today I'm going to talk to you about the relative performance of the site heterogeneous cat models and partitioning and handling substitutional heterogeneity for inferring accurate phylogenies. I should start off right off the bat that don't confuse these cat models with the cat approximation for accounting for rate heterogeneity in RAXML. These are the site heterogeneous models implemented in Phylogenomics. I'll talk about that a little more. So this is going to follow a little bit of a non-traditional format, so I'll kind of just hit the outline real quick so you're not confused. I'm going to give an introduction to kind of handling substitutional heterogeneity with some common methods that we've got currently. A motivation for a simulation study we did to actually look at how these methods compare and perform. Talk about how the different methods actually categorize heterogeneity and the accuracy in which they did that. Accuracy of tree inference, which I think is probably what most of us are really interested in this room. And then I'm going to give some conclusions and then recommendations for future studies, specifically for inferring accurate trees with large phylogenomic data sets. So substitutional heterogeneity has been known to be a problem for some time now. We have two papers up here by Brown and Lemon 2007 and Kanier and Lanphier from 2014, I believe, or 2015, that argue that we should be partitioning our data sets and accounting for substitutional heterogeneity in some way, shape, or form. Whereas Philippe et al. 2011 and some other papers really argued that site heterogeneous substitution models should be used for phylogenomic inference. So, given an introduction to these methods, data partitioning is widely used. It's relatively computationally efficient. Site heterogeneous models, I'm going to be focusing on the cat models that are implemented in a Bayesian framework in Phylobase. The reason I'm going to be focusing on these is because they are by far the most commonly used site heterogeneous models. These are very computationally demanding, notoriously so, where they don't typically converge on very large data sets. And so kind of what's going on here, with partitioning, you're blind to intragene heterogeneity, unless maybe you split up by codon positions. But you've got to feed a priori blocks, whether that's gene or codon positions or some other kind of partition. And you might use a program like Partition Finder to find the best fit partitions given your data and then assign those models. So that could be grouping genes 1 and 2 together and then genes 3 and assigning a fixed site homogeneous substitution model like WAG or WAG plus gamma or LG. Whereas, at least in theory, the real advantage to a site heterogeneous model is that it can see within gene substitutional heterogeneity. So it might give a category partition here, demarcated in blue, where it crosses genes, it's within genes, and then partition 2, category 2 would be the amino acid positions in red. And the CAT-F81 model, and you might hear this oftentimes referred to as just the CAT model, assigns an F81 model to each partition. So this one partition and then partition 2. CAT-GTR would assign a GTR model to each category or partition. I think generally people recognize that CAT-GTR is probably more realistic and arguably probably more accurate than CAT-F81, but the problem is that it's very computationally efficient. So people usually use CAT-F81 for inefficient. So people use CAT-F81 as kind of a faster method when CAT-GTR won't converge. So usually when you run an actual analysis using partitioning or the CAT models, you typically get a very similar tree with both methods. But the problem is that when you don't, it's been some pretty high-profile cases, especially animal evolution, which really affect our understanding of how animals have evolved. So for example, the placement of xenocoelomorpha, this is the A seals and xenotribellids. Typically cat models, although there are some exceptions with some recent papers, cat models would generally recover xenocoelomorpha sister and ambulocarya, so that's the hemichordates and echinoderms. Whereas partitioning and some recent analysis with cat models would recover xenocoelomorpha sister to all other bilaterians. And kind of where I got really interested in this is the kind of the debate between what's our most distant animal relative, whether it's sponges or ctenophores. Usually, at least up until very recently, cat models would recover sponges sister to all other animals, whereas partitioning or a single site homogeneous model would recover ctenophores sister to all other animals. And this fact has really been the workhorse for postulating about the accuracy of the cat models. But I would argue that given kind of the controversy of the placement of ctenophores and sponges, this probably isn't a very good data set to be using for arguing about the performance of a model. We're essentially basing our assumptions about model performance on a pretty tenuous assumption about the empirical phylogeny, which of course can't be known with certainty, the true phylogeny that is. So we wanted to do a simulation study where we actually know the answer with certainty. So we simulate 26 amino acid data sets with 5 different substitution models, so there's going to be 5 different, substitutional categories. I'm going to be pretty light on the methods, but I'd be happy to discuss this with anybody who's interested afterwards. And we did this on a variety of tree shapes with different taxa and what have you. We did model testing in Partition Finder. For some of our smaller data sets, we used the greedy search in Partition Finder. Larger data sets, we used relaxed clustering and 20% relaxed clustering. The relaxed clustering method in Partition Finder has become somewhat popular, especially for large phylogenomic data sets, making it much more computationally tractable than the greedy search. For partitioning, we inferred our trees in RaxML, and then we did analyses with the 2 different cat models in Phylobase. We used 2 different programs because you can't really do partitioning in Phylobase, and we used over 42 CPU years of computational time, and so we wanted to use RaxML kind of for efficiency. 97% of that time was spent with Phylobase, so that was kind of why we used these 2 different programs. And RaxML is still arguably one of the most widely used programs for phylogenomic inference. So let's look at how these models actually categorize, these methods categorize heterogeneity. So when we look at just a regression of total amino acid characters against inferred substitutional categories, so the x-axis is total amino acid characters, categories are on the left, on the y-axis. There wasn't a significant relationship with CATF81, but in every situation it overestimated the total number of substitutional categories by quite a bit. This would be CAT-GTR, that red line is the correct number of substitutional categories. And while it does get some of it right with some of these smaller data sets, it scales really significantly and very strongly with data set size. So this model, instead of actually seeing the amount of substitutional heterogeneity that's actually present in the data sets, it's actually just inferring categories based on how much character data is in the matrix. Partition Finder, the greedy search, there was a positive relationship that was significant, although the relationship was weak. And it's worth noting that it did nail the inferred number of substitutional categories in most of the situations. The larger data sets where we did 20% relaxed clustering, there wasn't a positive relationship, but it did overestimate the number of substitutional categories. I should point out, if we let this run, I did this on one data set, it took quite a while, but if you run one of these larger data sets using the greedy search, it also nails it perfectly. So I think that's worth noting. But still, this is computationally effective. It's still not doing perfect, and I think that's worth noting. But what I think most people in this room are probably interested in most is tree inference. So how do these models actually do when we knew the true tree? Well, CAT-51 did really poorly across the board. It typically inferred sometimes incorrect relationships, as indicated by this polytomy that's in red. And correct relationships were oftentimes inferred with weak supports. So these are posterior probabilities. In contrast, when it actually came to inferring the correct tree, CAT-GTR partitioning did rather well, and similarly. But generally, CAT-GTR inferred worse branch lengths than when using partitioning. And I'll get at why that might be the case in a moment. We also wanted to look at two empirical data sets which have really been the workhorses for arguing why cat models are, the greatest thing since sliced bread, really. And so we took a look at these and tried to look at some results when we reanalyzed them in the context of simulation. So in the original studies, Philippe et al. 2009 used CAT-F81, they didn't use partitioning or CAT-GTR, they recovered Sponge's sister. Nosenko et al., CAT-F81 recovered Sponge's sister, CAT-GTR, they kind of got this unresolved basal polytomy, and they didn't do partitioning. Now, when we inferred, when we took the same data set Philippe et al. 2009 used and used partitioning, CAT-GTR, and CAT-F81, we inferred Tina-4 sister all their animals with all three models. So not only is this kind of interesting just as far as like an animal evolution perspective, but it's also worth noting that kind of fits what we saw in simulation. We're typically getting similar relationships. With the Nosenko et al. 2013 data set, CAT-F81 recovered Sponge's sister, whereas CAT-GTR partitioning recovered Tina-4's sister. And so, in the context of our simulation results, we can kind of look at that and say, okay, well, in simulation, CAT-F81 looked inaccurate. That's probably not the right topology. So, it would seem that matching kind of our simulation results, CAT-GTR and partitioning got the same answer, which is T enforced sister to all their animals. Now, one of the things we looked at is as far as each category that CAT-GTR inferred. On average, most of these data sets only assign 28 or less than 30 amino acids to each of these categories. That's far too few amino acids to inform a GTR matrix with any degree of certainty. This is probably why it's not doing that great at inferring branch lengths, and it's potentially why CAT-GTR is really slow to converge, because these individual GTR models are clearly over-parameterized, which we know can slow convergence. So I'm going to hit on some conclusions and recommendations. So CAT-F81 is inaccurate. I think that's pretty clearly demonstrated. I would argue that partitioning works as well or better than CAT-GTR. CAT-GTR is prone to over-parameterization, at least those individual GTR models. And then I'll just harp on this because this is something that I'm very interested in. The available evidence really suggests that ctenophores are our most distant animal relative. And I'd be happy to talk any more with anybody who's interested about that as well afterwards. So, recommendations, I think given the models that, among the stuff that we commonly use, I think that partitioning is giving us accurate tree inference. I think site heterogeneous models are great in theory, but we need to actually make sure they're performing well. And I would say that this could be done in either a likelihood or Bayesian framework. So models and methods, I think they need to be tested in simulations before we really start running with them. And I would say that more broadly, trees inferred with CAT-F81 should probably be revisited, especially when they've disagreed with trees inferred with other methods. So with that, I need to acknowledge the Alabama Supercomputing Authority and NASA for funding, Milton Tan and others at Auburn University out of Advanced Ideas Alpha, and the members of my lab at Auburn University. I think I have about a minute or two for questions, so yeah. Yeah.
So for the empirical analyses where you have different trees, different approaches, do you make any attempt to assess the model accuracy?
So we didn't really look at that. The main reason is that typically when they look at model fit for the CAT models, they use a cross-validation approach that's implemented in Phylobase. And so comparing partition models versus the CAT models has never really been done. But that's something that I think I'd like to see developed, and so we can do it.
Talking about maybe something like posterior predictive simulation to assess the capacity of the competing models.
Yeah, so we could do that if we did partitioning in the kind of a Bayesian framework as well. I think we did that, but we didn't look at that.
So without knowing